Hello everyone, let's tackle a new method of solving electric field, still under electrostatics topic. As a review, we know that electric field intensity due to a point charge is given by this equation. E is equal to 1 over 4 pi epsilon naught q r squared and unit vector r hat, where r hat is a unit vector in the direction of increasing r. Okay? So if we want to add electric field due to the number of point charges, then the equation applies the principle of superposition, which is equal to the resultant E is equal to E1 for charge 1 plus E2 for charge 2 plus all the charges up to charge n. Okay, so this is very difficult. Now just imagine you're going to add all of these charges. Or the electric field due to this or number of charges. However, if the distribution of charge is continuous, take note, if it is continuous and spread, or it is spread uniformly to asymmetric surfaces. Example, a spherical surface or cylindrical surface. So we can use an elegant manner of calculating the resultant electric field. So this alternative method is known as the Gauss's law. But before tackling the Gauss's law, first we need to define an area vector. Area vector. So don't be confused with this term, because basically area is a scalar. But we need this term to represent a surface and direction of the field lines. So this area vector represents a surface by a directed line segment erected perpendicular to it and the magnitude equal to its area. Okay? Here are a sample of unit area vectors. Okay, but in terms of direction, as you can see, there are two possible directions. Okay, the direction can be in this direction or the other way, the opposite direction, since it's a surface area. So two possible directions to a surface element. The red line denotes the other possible direction of our surface element. And then this surface element actually is just part of a larger surface that encloses a large volume. So just a small element. So we can take the direction in our area vector as out of the volume enclosed by a surface, or towards, out or in. So let's consider, for example, a point charge located at the center of an imaginary spherical surface of radius r. Yes, in this drawing, okay, note that a small portion of a spherical surface, this one, is not flat. But if we choose our area whose length and width are so small, so it will approximately become a flat surface. So another thing to note is the equidistant points from the charge to the surface, since our imaginary surface is spherical. So R is the same all throughout. No? Thus, in this case, RE will have a constant magnitude. Take note, E is constant in magnitude based on our sample. So our E will have a constant magnitude over the surface, and all will be perpendicular to this small area element denoted as dA. And we also consider that since our object or our charge is positive, then our electric field or electric field line direction is outward or away. Okay, let's continue. So let's label delta phi is equal to the product of our electric field and our area, small area, dA, or the small element. Okay, then taking all the sum of this delta phis over surface to get phi, then this is equal to summation of delta phi over surface, or this is summation of EDA over surface, or this is summation of ETA is just equal to 1, since E is equal to 1 over 4 pi epsilon naught Q over R squared TA, since this is equal to E, or where our A is just the index of summation. Okay, so let's label this as RA in here. So RA is the index of summation. So indicating that the sum is over the total area bounding the spherical volume. So the total surface area. So therefore, if we limit our dA to approach 0, our equation becomes the limit of 1 over 4 pi epsilon naught Q over R squared summation of dA. And since this equation 1 over 4 pi epsilon naught QR squared are constants for spherical imaginary surface, take note that E is constant, then our equation becomes the integral over closed surface E dA. Okay, and this is equal to 1 over 4 pi epsilon naught Q R squared integral of dA, or this is just equal to 1 over 4 pi epsilon naught QR squared times 4 pi R squared. Why? Because this 4 pi R squared is just the sum of all the dA over the sphere, or simply the area of spherical surface, right? So thus our equation that epsilon naught closed integral of EDA is just equal to the total charge enclosed. And this equation is known as the Gauss's law, defined as the surface integral EDA is just equal the charge enclosed by the surface. So in this equation, Q is the net charge. So Q is the net charge. So for example, if the enclosed charge is 2, or two equal and opposite charges, then the net enclosed is zero. But it doesn't mean that electric field is zero in the region. Only the enclosed is equal to zero. Let's try a sample problem. We have in here example 2-point charges Q1 and Q2 separated by a distance r. So we use the spherical Gaussian surface in here. Let's apply the Gauss's law. Now, by definition, epsilon naught integral of E dA is equal to Q1, our enclosed surface. And since our integral dA is just a total, the total of our area enclosed, so, and also E is constant. So taking E outside of the integration, dA is just equal to Q1 epsilon naught. And so E, and then this surface area is just equal to the spherical surface, 4 pi r squared, equal to Q1, the enclosed charge, over epsilon naught. Or E is just equal to 1 over 4 pi epsilon naught Q1 over r squared. And what have you noticed in this equation? This is just the equation for an electric field intensity experienced by the charge Q2, right? So the corresponding force experienced by Q2, on the other hand, due to Q1, thus becomes F is equal to E Q2. What happened to my pen? Or therefore, this equation becomes 1 over 4 pi epsilon naught Q1 Q2 over r squared. This is just, again, the Coulomb's law. So this leads us back to Coulomb's law. Our previous example shows cases where E intensity is parallel or antiparallel to the area vector. In general form, the Gauss's law expressed in this manner, that epsilon naught of the integral E dot dA is equal to the charge enclosed. This is the general form. Because not in all cases that our surface area is directly or parallel or anti-parallel to our electric field lines. Anyway, let's consider another example. For our example number 2, so calculate the electric field intensity due to a long straight charged wire. So imagine the wire to consist a large number of point charges. So obviously, superposition principle of adding E's or electric field due to each charge is not easy. So Gauss's law helps simplify this very tedious work. So from our figure, we expect that E or electric field will be directed radially outward from the wire since it is composed of positive charges. And then take the length to be L for the length of our Gaussian surface. Now our Gaussian surface is cylindrical. And our E, or electric field, is always parallel to our area vector. We already defined our area vector. Direction is line segment erected perpendicular to small surface area. So thus, in our cylindrical cups, or a cylinder cups in here, two cylinder cups, our E is just equal to E dot dA for the caps is equal to 0. Why? Since E and surface area vector are perpendicular with each other. And take note, that product, the dot product is cosine theta. So by definition, your previous physics, the E dot dA is just equal to E dA cosine theta. So therefore, automatically, our E dot dA for the caps equal to 0. Thus, our equation for E total is equal to, or simply our epsilon naught, the integral of, or closed integral of E dot ds, or dA, surface area, is just equal to the epsilon naught integral of E dA over left cap plus epsilon naught, the integral of E dot dA over curved surface plus epsilon naught integral of E dot dA over right cap. And this is equal to the Q enclosed. Okay? Therefore, our epsilon naught integral of the closed surface A dot dA is just equal to the epsilon naught integral of E dot dA over curved surface. Why? This is 0 and also this one equals 0. And all of this equal to the Q enclosed. So note that the charge is distributed uniformly over the long wire. Thus, wire can be characterized by a linear charge density. Again, since it is uniformly distributed, then we can define the charge density. Let's define charge density as the lambda, or this is charge density, or this is the density or charge per unit length. So thus, lambda is equal to charge per unit length, or Q is just equal to lambda L. Okay. Therefore, our epsilon naught integral of E dot ds, or dA, surface area, dA is equal to the epsilon naught integral of E dot dA curved surface is equal to lambda L, or epsilon naught E integral dA cosine 0, since parallel, is just equal to lambda L. Therefore, epsilon naught E is equal to 2 pi RL equal to lambda L, where this quantity 2 pi RL is just the equivalent surface area of our cylindrical Gaussian surface. So thus, our electric field is equal to lambda L over epsilon naught 2 pi RL, or E finally is just equal to lambda over 2 pi R epsilon naught. This is now the electric field due to our linear charge density, or the electric field due to the straight charged wire. Okay?